Hi, and welcome to Lecture 11 of Math 1B03. In today's lecture, we're going to be looking at Section 2.1, which it talks about matrix operations. And in fact, that's kind of the main topic of today's lecture, is operations that can be applied to matrices. So we're going to learn a bunch of ways that we can take matrices and combine them to form new matrices. We'll learn about multiplying matrices together. We'll learn about adding matrices together. We'll learn about things such as like the transpose, and we'll be learning about some of the basic properties of these operations. As well, in today's lecture, I'm going to try to show you how you can also do these operations, implement them in Octave or in MATLAB if you're also using that. So let's jump right into the basic terminology. So a matrix is something that we've already seen here, but I'm just formally defining it again, is in a rectangular array of numbers. So we've seen this when we talked about the coefficient matrix of a system of linear equations. And the numbers that are inside of your matrix are usually called the entries. Now, when a matrix has a size, and we usually describe the size of the matrix by the number of rows by the number of columns. For example, it's very typical to say A is an m by n matrix. So what we mean by this is that A is a matrix with m rows and n columns. So it's very important that you keep the order, keep these two numbers in the correct order. The first number represents the number of rows, the second number represents the number of columns. Now we need to be able to identify specific entries in our matrix, and the way that we do this is we denote an entry in row I, column J, by A sub ij. So the first index tells me which row I'm looking at, the second index tells me which column I'm looking at. And more generally, we may sometimes write wrong thing, use my hand here. More generally, we may talk about a general matrix. If I would just want to represent a general matrix, this is an m by n matrix. Here I have entry 1, 1 in row 1, column 1, entry A1, 2 in row 1, column 2, and so on. So I can represent my m by n matrix in this form. And I also may represent my m by n matrix as a series of n columns. We've seen this before in some of our previous lectures. Or we may write it in a short form where we write A sub ij just to mean that these represent the particular entries. So there's a bunch of different ways to represent a particular matrix. And let me just give you an example of some of this. So I'll go over to my example here, and I can write here A as the matrix 1, 2, 3, 3, 4, 5. And so this is going to be a 2 by 3 matrix because I have 2 rows and 3 columns. Now, one of the things we want to be able to do in this course is manipulate matrices. And so you've already seen this probably in some of your labs, and this may be kind of review depending upon where you are in the course, but you can implement, or not implement, but you can input a matrix into Octave, and here would be the command. So A is equal to A 1, 2, 3, 3, 4, 5. Okay, so this is a semicolon here to represent a new row. And so let me just kind of break out a full screen here and go to Octave. It looks like it went to sleep on me, but let me reload it. So here I will put A is equal to 1, 2, 3, semicolon, and what did I have? 3, 4, 5, 3, 4, 5. And there gives me my matrix. And I should be able to pick out a particular entry. Hopefully I get the index right here. 1, 3. Oh, sorry, I want. So what this is telling me is in row 1, column 3 is the value 3. So it's picking up this value and this entry right here. So this is how I pull out a specific entry of my matrix. Let's go back to my file here. Okay. Now there are some very special types of matrices that are going to show up a lot in our course. We have what's called a square matrix. And what is a square matrix? Well, that's just simply an n by n matrix. The number of rows is equal to the number of columns. A diagonal matrix is a special type of square matrix, and this is a square matrix of the form. Here, so I'll write myself a square matrix. And this matrix has the property that all of the entries off of the diagonal are 0, and the non-zero entries show up on the diagonal. So that should be n sub n. Hopefully you can see that. And then all of these entries over here are 0, and all of the entries over here are 0. Now these entries here can or may not be 0, but to be a diagonal matrix, all the entries on this side and all the entries on this side must be 0. And an identity matrix is just a special type of diagonal square matrix. It's the matrix where we have all ones down the diagonal. And we've actually seen the matrices of this type before. We have I3, for example, it would be this matrix right here. So it's a 3 by 3 matrix. We have ones down the diagonals and zeros everywhere else. So that's the identity matrix, and we'll see it appear a couple times more in today's lecture. And then we have a zero matrix, and this is simply a matrix with all zeros. Now, we don't require that a zero matrix be square. A zero matrix can be any size. The only requirement is that every entry be 0. And of course, you can input all of this information into Octave quite easily. Octave and MATLAB is a little cute when it comes to defining the identity matrix. So for example, if you input I3, what they're doing is they're being cute. Here the word I is supposed to represent I. So let me just go back over to my MATLAB, hasn't gone to, or my Octave, excuse me, and I input I3 and outputs the identity matrix. I could also do I4 and it will give me the 4 by 4 identity matrix. So it's being a little cute there. That's how you get the identity matrix. Let's say you wanted to get the diagonal matrix. Well, here's a quick way of getting that. You can define, it looks like a 1 by n matrix where you put your values that you want on your diagonal, and then you let D equal to the diagonal of V. So let me give you an example of that before we take a short break. So let's say I take my vector V to be 1, 2, 3, 4, 5, and let's say 20, 20. And so I'm getting a 1 by 6 matrix, and now I will ask for the diagonal matrix with V. So there I have now a diagonal matrix. Here I have a diagonal matrix where my entries are 1, 2, 3, 4, 5, and 20, 20. Okay, so we will talk a little bit more about other operations we can do on a matrix in a minute.